Yeah, so thank you very much for the introduction and for the invitation to this conference. So the goal of my talk somehow is to speak about two modularity results related to Higner divisors. The one is the Gross-Cohn-Zage theorem, and the other one is the result first proved by Don Zagier on the modularity of traces of singular moduli. And I guess the main goal is to find some common framework how this fits together. Okay, so most of what I'm going to talk about is joint work with Yin-Kun Lee. And I want to start with the Gross-Cohn-Zage theorem. So this is a result about the modular curve x0n. So we start with the modular curve x0n. And it is a result about Higner divisors on this curve. How do you define these Higner divisors? There are different ways of defining them. Basically, you've seen them yesterday in Scott's talk, where they already appeared. One way of defining them is to use the modular interpretation of this curve. So you can say this parameterizes cyclic isogenies of elliptic curves of degree n. And then, so every point on the modular curve corresponds to a cyclic isogeny of elliptic curves of degree n. And then, in general, elliptic curves have as their endomorphism ring just the integers, at least here in characteristic 0. But then sometimes this endomorphism ring can be larger. This is when you have complex multiplication. So you can look at the special points corresponding to elliptic curves with complex multiplication. So you can look at a negative discriminant. So negative d should be the discriminant of an imaginary quadratic field. So it's a discriminant. Or more general, discriminant of an order in an imaginary quadratic field. And you assume that it satisfies the Higner hypothesis. So it's a square mod 4n. And then you can look at the Higner divisor of discriminant minus d, or, well, let me just say of discriminant d. So d is positive. And this is given by, so you sum over the points in x0n where this corresponding cyclic isogeny has complex multiplication with the order of discriminant d. So this should contain O minus d, where O minus d is the order of discriminant minus d in the imaginary quadratic field q root minus d. And then you sum the corresponding points here. And you weight by the number of roots of units in this order, and in that way you get a divisor which is defined over the ring class field of this order in this imaginary quadratic field on the modular curve. And then you want to look at the class in the Jacobian, so you want to get a divisor of degree 0. So what you do is you define ZD0 to be z of d minus degree of this divisor times some distinguished point, and then usually, I mean, one thing you can take is you just take the cusp at infinity, and then you get a divisor of degree 0. I mean, these degrees are basically like Hurwitz-Kronecker class numbers, so they are something not too complicated. Alternative way of thinking about those is you take, so this is, as you saw in Scott's talk, you take quadratic forms of discriminant negative d, or the gamma 0 n equivalence classes. And then for all of these quadratic forms of negative discriminant, you have a unique 0 in the upper half plane. And then you take those points, and they give you, so those points for a fixed discriminant, they give you then these Heegner divisors on this modular curve. All right. Now we're basically ready to formulate this Gross-Cohn-Zage theorem. So somehow these divisors, these Heegner divisors, they define classes in the Jacobian of this modular curve. And you can ask yourself, what are the relations among these divisors, rational relations, or what are their positions in the Jacobian? And this Gross-Cohn-Zage theorem very elegantly encodes all these relations by saying that the generating series of these guys is modular. Okay, so it says that if you write down a generating series, so you sum over the positive d such that you have this Heegner hypothesis, so minus d should be a square mod 4n, and then you take the class here of these guys, CD0 in the Jacobian, so you form a generating series, and then it says that this is a modular form of weight 3/2 with values in the Jacobian of the modular curve. So here somehow the Jacobian of x0n. So in other words, whenever you have a functional on the Jacobian, you can apply it coefficient-wise to this generating series. So you get then some Q series here with complex numbers as their coefficients, and then the statement is that this Q series is really a modular form of weight 3/2. Okay, so this is a very nice result and very much related to the Gross-Zage formula on the canonical heights of Heegner divisors, well, which is of course a very important result. Okay, then there is a related result. So this was somehow in the 80s. Then there's a much more recent result due to Zage on singular moduli. So also want to talk about that. So what are singular moduli? So these are the values of the J function at CM points. So at the points that appear here in these Heegner divisors. So in this case, I want to assume that n is 1. So before n was general. And by the way, I should also point out that I'm being a bit slobby with the level of these modular forms. So somehow if you write it down this way and you want that literally to be true, then here you have to work with gamma 0 4n. But then this is maybe not the best way of phrasing it. It's maybe more natural to work with vector-valued modular forms, and then you can get to the full metaplectic extension of SL2Z, or you can phrase it in terms of Jacobi forms as you like, but that's not really that important for this talk. Okay, so singular moduli. I want to look at n equal to 1. So here we're just looking at the modular curve x0, 1. So this is just P1. And we want to look at J. So J of tau, the usual J function, E4 cubed over delta. And, well, this has some Q expansion, Q to the -1 plus 744. And then next term is something like 196884Q, and then plus higher terms, so usual J function. And somehow it's more convenient to look at the normalized Hauptmodule, which means that we want to subtract the constant term. And then we want to look at singular moduli here, so we want to look at the CM values of this guy. Maybe let me, maybe I'll write this here. I can keep it for a little while. So I can look at the trace of this capital J of discriminant D, which is defined as the sum over the Z in the support of this Heegner divisor and on the modular curve. And you weight again by the number of roots of unity in the order of discriminant D. And then you evaluate J at the point Z. So you basically, you evaluate J at this divisor, at this Heegner divisor. And then because the divisor is defined over the ring class field of this order, I mean, all these guys are basically conjugate to each other and contained in this ring class field. And then here you take basically a trace. So what you see is that this is really some integer. And you can look at these numbers. And in particular, since those are, again, naturally indexed by D, it's again natural to form a generating series. And then you can ask whether this thing is modular. And then there's the theorem that Don proved. Well, he looked at the modular form G of tau, which is basically the generating series. So not quite, but basically the generating series of these traces of discriminant D of the capital J, Q to the D. And so somehow it turned out that this is not the right thing to look at. You actually also have to put some pole at the cusp. So what you really have to do is you have to put a Q to the -1 here, and also have to put a -2 here, some constant term, and subtract this stuff. And then what the theorem states is that this is modular. But now, since we have a pole here at the cusp, this is only weakly holomorphic. So theorem is that this guy is weakly holomorphic. So I use Don's notation here with a shriek. This is weakly holomorphic of weight 3/2. And it's actually easy. You can write down an explicit formula in terms of eta and so on. So this gives you actually a very nice way, in some sense, a formula for those traces in terms of modular forms. Okay, so this is this result of Don. And this sort of triggered a lot of further research on this topic. So there is work by actually many people who generalize that in various directions. So let me just mention, I don't know if I'm able to do it in chronological order, but at least I can try. So there is work by Jens Funke and myself. So then there is work by Bill Duke and Paul Jenkins. There is Bringman Ono, for instance. There's work by Claudia Alphes and Stefan Ehlen. And, well, many other people that generalizes these results in various directions. So for instance, here in the Funke-Brunier paper, so this is actually the result that Scott was mentioning in his talk yesterday. So this realizes somehow this little g as a Kudler-Milson theta lift of the capital G. And then once you have it as a theta lift, you can generalize to arbitrary level rather easily. So this generalizes to arbitrary level and also to harmonic mass forms. And then those works here consider generalizations to higher weights, and also other weights, and investigating various properties. And Alphes Ehlen, they also look at twists with genus characters and things like that. So there's quite a bit of work on this topic. And but still some things are a little bit puzzling. So of course you wonder what is the relationship between the two results. I mean, here we have this generating series. This is modular of weight 3/2. Over there it's similar. So it's kind of similar, but still it's not the same, because here you really get holomorphic stuff, or in fact it's actually cuspidal. So this is a cusp form, whereas here this is, well, clearly just weakly holomorphic. Also you get here this constant term that you don't really understand that well. I mean, there's some interpretation in the paper that I have with Jens, where we interpret that as sort of some average value of J. But still, it's also, if you look at the proofs, I mean, the proofs that we have for this result basically don't work in that case and the other way around, so it's a bit confusing in some sense. But then there was a very nice idea of Dick Gross that one could interpret these traces of the capital J in terms of a generalized Jacobian. So that was his idea. And this gives then some interpretation in some sense of this result of Don in a more arithmetic or geometric way that sort of is more naturally related than to Gross-Cohn-Zaghe. Somehow the point of my talk is that one can use this idea to somehow, I mean, this idea carries much further. So it gives a general framework. It also gives, in this general framework, one can sort of prove some abstract modularity result that somehow includes both of these results as a corollary. In some sense, it gives unified and, well, depending on your point of view, simple proofs of all of these results. And maybe using these ideas, one can also look at higher dimensional generalizations and things like that. So somehow I want to look at a common framework for this stuff. And what we do is we look at a generalized Jacobian. So what is this? Let me remind you or explain what that is in a few words. So if we have an algebraic curve over a field of characteristic 0, it should be complete and non-singular, so it should be nice. So somehow the complex points, really nice, compact Riemann surface, such as x0n. So you can just think of x0n. And then we can associate the Jacobian of this curve, J, of x, which is an algebraic group over K, and the K points correspond to divisor classes defined over K modulo rational equivalence. So this is basically like a divisor class group. Okay, but then we can refine this notion and look at the generalized Jacobian, and to define that, you pick some extra data, which is an effective divisor on this curve. So you need an effective divisor on this curve, and today, for simplicity, I want this divisor actually to be just a multiple of a point. So I take a point defined over K, and I take a positive integer, m, and then I can look at the divisor, which is now math frac m. So this is m times y. So this is a very simple effective divisor on this curve. Okay, and now I can look at not only at rational equivalence between divisors, but rational equivalence by divisors given by rational functions that satisfy some growth conditions at the points in this effective divisor. So I define P sub m. So this should be divisors of rational functions. So f is a rational function. And this should have some prescribed growth. How should it look like? So it should be like, I mean, this f could have a pole at the point y. I somehow want to multiply away the pole. So I take a local uniformizer at y to the power given by the order at y of f times f. So now this starts somehow the expansion at the point y now starts with just some constant. And it should be like 1 plus, and then nothing, and then only terms of order at least q to the m, pi to the m. Later, pi is going to be q, some more local parameter at a cusp at infinity, so you can think of it that way. So somehow the expansion of f at y should, I mean, there should be some leading term, then there should be nothing, and then there should be terms of order pi to the m again. Okay, so we can look at that. This is some group, and then we can look at the generalized Jacobian. What is this? This isn't just as the usual Jacobian. It's an algebraic group over k, commutative, and the k points correspond to classes of divisors of degree 0 defined over k modulo divisors in this group P sub m. So J m, yeah? No, because I mean you can always multiply f by something in k cross without changing the divisor. You know, so you could here put here a constant in k cross, but that doesn't really matter because you can always multiply the function by a constant, right? Yep, that's right. But here I only have 1 point, right? So there's just y. If you do this more general, then that's right. Then you have to put here a constant, but that's correct. Yeah. Okay, so Jm of k. So this should be just divisors of degree 0 on x mod Pm of x. So this should be the k points. So it's like a slightly refined divisor class group. So that's all that it is. And then there's a natural map, of course, from so I have a natural map from this generalized Jacobian to the usual Jacobian. Yeah, because here, so somehow, if I have a divisor class here, so then I can just look at the class of the corresponding divisor in here. So this just means I factor out more rational functions. So I somehow forget this extra condition. So there's a natural map, which is surjective. And the kernel of this map is just given by the additive group to the m minus 1. So and you can somehow write down explicit generators for the kernel. So what can you do? So you can take, so this is generated by classes as follows. So you look at functions hn. So these should be rational functions on your curve, which at y behave like, so they start with 1, and then the next term is pi to the n, and then there are some higher order terms. So there exist functions of this type for n for any positive integer n, you can do that. You can find such a function. So that's easy to see that this is possible. So some rational function with this growth behavior you choose, and then you can look at the class of this guy. So I want to denote the class of this guy then in the generalized Jacobian by these brackets sub m. So this defines some class, and those classes generate the kernel when n goes from 1 to m minus 1. And in that way you get somehow this, so you see that the kernel is what I wrote down. Okay, so these are kind of important, these things, later. Okay. Now I want to use this setup in our case. I want to look at classes of Hegner divisors. Oops. So now x should be just the modular curve x naught n. The distinguished, which is defined over Q. So in some sense, if you like, K is Q here, field of definition. The distinguished point Y, I want to take the cusp at infinity. And then the local parameter, pi, at the cusp at infinity is just the usual Q, which is e to the 2 pi I z, with z in the upper half plane, or if you like to think about it more arithmetically, it's a parameter that occurs if you look at the Tate curve. And for this effective divisor, the frac m, I then take the usual m times the point at infinity, where m is some positive integer. Okay, and then I can define classes or look at the classes of these Hegner divisors in the generalized Jacobian. So I can look at, for d positive, I can look at z d0 and then take the class in the generalized Jacobian. So this is going to be then in J m of x, q rational points, which I want to, I don't want to write down the points because it's always going to be q now from now on. So this is for d positive. You have those classes. But now you can also define classes for d0 and d negative as follows. So for d0, what you can do, you take z of 0, 0, kind of stupid. This should be just the class of the line bundle of modular forms of weight -1. So I should say that also for this generalized Jacobian, if you have a line bundle on the curve, then there's a well-defined class in the generalized Jacobian, and here you take the class of the line bundle of modular forms of weight 1 in this generalized Jacobian. So this is in here again. And then you can also do something for the negative d. Maybe I'll write this here. So if d is negative, what do you do there? Well, basically there are two cases. So one case is the case where d is minus n squared for some positive integer. So it's minus a square. And there you take the divisor of this function hn. So the function that we choose, whose Q expansion, oh, so somehow this is not so nice. Somehow I used pi and q simultaneously up there. It's not so great. Should correct that. So somehow here we take now the divisor of this function hn. and then the class and the generalized Jacobian if D is of this form, and otherwise we just take 0. So this is otherwise. So in some sense, no. Oh. So in some sense, it's quite nice to have these extra functions in the that you have when you work with this generalized Jacobian, because using those we can define extra classes in that way. Okay, in that way we have for every integer a class of divisors in the generalized Jacobian, and now I guess it's pretty clear what the first main result is. So the theorem then that we can prove here is that if you write down a generating series of those guys, then you get something modular. So somehow the generating series AM of tau, where you now sum over. So I should also say maybe that if n is bigger than, so if n is at least m, then somehow the pi to the n sort of can be absorbed in the O of pi to the m. So in some sense, this is, in that case, the divisor of this Hn is just 0 in the generalized Jacobian. So somehow here, if you work with that, then you only get non-zero classes if n is less than m. So in that sense here, for the generating series, you only need to sum over D that are bigger than minus m. And then you put the classes Z of D, 0, m, and then you put Q to the D. So this is a priori just a formal Q series with coefficients in the generalized Jacobian, and the statement is that this is modular. So this is a modular form of weight 3/2, weakly holomorphic. Wait. Summation index. So minus m. No, I think. Yeah, so there is some bound. Yeah, that's right. Let's see. No, it's Hn, and yeah. So I think it's right like that. I mean, you have. So say if D is -1 or -2, then let's see. I think it should be fine. I think it's okay like that. Maybe you're right. You're right. Thank you. Now I understand. Yeah, so maybe there should be a square. Yeah, thank you. Confusing. Okay, so in any case, this is a modular form, and it has values in this generalized Jacobian. Okay, what does this mean? This means whenever you have a linear map from the generalized Jacobian to the complex numbers, then you can apply it to this thing coefficient-wise, and you get something which is modular of weight 3/2. Okay. What can we say about the proof? So what do we gain in that way? So in some sense, the proof, for the proof of this, one can adapt an argument of Borchert's to prove the Gross-Kohn-Zage theorem. So what can you do? You use a lemma for proving modularity, and the lemma, many of you will know a variant, I'm sure. So if you have so this is now a G that doesn't have to do anything with Dons G. So this is just now some formal Laurent series. So a formal Laurent series. So you can write down formal Laurent series of this type. So we allow negative terms. So D0 could be negative. And this guy has complex coefficients. And now you can ask yourself, when is this the Q expansion of a modular form? So this is in the space of modular forms, weakly holomorphic modular forms of weight k, if and only if a nice pairing with forms of dual weight is 0 for all forms in dual weight. So this is true whenever the sum over d bigger than d0, c of minus d, b of d is 0 for all forms f with Q expansion c of d. In the space of weakly holomorphic forms of dual weight, which is 2 minus k. So this is this lemma, which is also used by Borcherds in his proof of the Gross-Kohn-Zage theorem in a variant where he actually uses here formal power series instead of Laurent series. But if you look at the proof, which is some application of Serre duality, you notice that by twisting things with a line bundle corresponding to the cusp at infinity, then basically the same proof goes through and you get that result. So you can detect modularity using this pairing, and this is what I want to use to prove the modularity result here. So proof of the theorem. What do we have to do? So if we want to apply that, then we have to show that for all weakly holomorphic forms of dual weight, so what's the dual weight? So somehow here we claim modularity in weight 3/2. So the dual weight is then 2 minus 3/2, which is 1/2. So for all weakly holomorphic forms of weight 1/2, so F with Q expansion coefficients C of D, Q to the D of weight 1/2, weakly holomorphic, we have a relation like this. And the G is now our A sub M. So what do we have to show? We have to show that using these coefficients of the F, we have the relation that the sum over the C of minus D times now the class of the this Hegner divisor in the generalized Jacobian, and D goes from D0, that this is 0. But now this is a linear combination of classes in the generalized Jacobian, so this should be really 0 in the generalized Jacobian. Maybe up to torsion, so you can tensor with Q or C or something to kill the torsion. Okay, so this is what we have to show. And how do we do that? Well, we use the fact that if we have such a guy of weight 1/2, then there is a Borcherds lift that gives a section of a line bundle of modular forms with known divisor somehow. So this is similar as in Borcherds' proof of the Gross-Kohn-Zage theorem, except for the fact that we use more properties of the Borcherds products. So use Borcherds lift. Of F. So what is this? This is some meromorphic modular form on the modular curve x that has some product expansion. So this is some function psi of f. And let me write down the q expansion of that. This is given as an infinite product with some leading term q to the rho, where rho is some rational number. And then there is a product over positive integers. You have 1 minus q to the n, and then you have c of n squared in the exponent here, where the c of n squared are coefficients of this f. So the Borchardt-Swift of f is meromorphic modular form. It has such an infinite product expansion. The weight, let me put it here, the weight of f is given by the constant term, so this is C0, and then the divisor on x of this guy, of this psi. This is some explicit linear combination of these Higner divisors, and then we have this infinite product expansion. So this is somehow this Borchardt-Swift. And what does it tell us? Well, the point is now psi is a rational section of the line bundle of modular forms of weight C0. Right? So this is the statement that this is a modular form of weight C0. So it's a rational section of, you can say, M, the line bundle of modular forms of weight minus 1 to the, so you take the C0th power and then the dual of that. So in some sense, it's related to the line bundle of modular forms of weight minus 1, which appears in the definition of this class of the C0. And then, well, now we can look at the class of this line bundle in the generalized Jacobian. And how is the class defined? The class is defined, you take a rational section that has a prescribed growth at the distinguished points in this divisor that you use to define the generalized Jacobian. So you cannot really take the psi. So this is not okay, because here the Q expansion, I mean, it's in general, if you think of the delta function, where you have a similar product, of course, first coefficient of delta is 1, and then the next one is minus 24, or something like that. So it's, in general, all coefficients non-zero. So we cannot take that one. But here, you see that if you divide this guy by these HNs, so these functions whose Q expansion starts like this, so this looks like the HN, actually then to this power C of n squared. If you divide out these HNs, then we get something that starts like Q to the rho plus, and then we have Q to the rho plus M. So then if we divide out by the HN for n from 1 to m minus 1 to the right power, then we get something that looks like something that we can use. So we take this guy, product n from 1 to m minus 1, and then we put hn to the c of n squared. So if we look at that, then this is going to look like q to the rho, and then we have 1 plus o of q to the m. So this has the right growth at the distinguished point, and so we can now use this to define to compute the class of this bundle. And how is it defined then, the class of this bundle? So we just take the divisor of this guy and then the corresponding class in the generalized Jacobian. And if you see what this means, then somehow these Hn, they give you then this Zd. This is related to the Zd, where d is minus n squared. And then this is the divisor of this guy is related to these Higner divisors. And if you work it out, then you see that the class of this guy is given by the divisor of this guy. And then if you work it out, it means that we have exactly this relation. Yeah? And this concludes the proof. And notice we've used all that we know about Borchards' products. We've used the information on the weight, information on the divisor, on the modular curve, plus the product expansion. Okay, so this is kind of nice. And one corollary is if we now take this generating series and apply the map from the generalized Jacobian to the usual Jacobian. Yeah, we can apply that to this generating series just by doing it on every coefficient. If we do that, then we get exactly back the Gross-Cohn-Zage theorem, right? And Gx, you say? Good point. Good point. Thank you, thank you. So if we apply that map, then we get back the Gross-Cohn-Zage theorem. Notice that for D negative, we have that this map takes the ZD in the generalized Jacobian, which is then non-zero in general, to 0. So these guys lie in the kernel. Yeah, so in that way, if you look at this generating series, it has some polar part that gets cancelled, and this explains why we get actually something holomorphic in the Gross-Cohn-Zage theorem and not weakly holomorphic. For D equal to 0, this also gets killed. Yeah, that's right. Because somehow we always project here on the degree 0 part. That's correct. Yeah. Okay. And I don't know. Maybe so time is up. 2 minutes. Okay. So in the remaining 2 minutes, maybe just here I briefly explain how to get Don's result, so the traces of singular moduli out of that. What do you do? Okay, so now let's take, so we have our modular curve and we have this distinguished point in there, the cusp at infinity we took. So you could also do this more general by taking not only the cusp at infinity, but say an arbitrary effective degree 0, no, that's a contradiction. You can take an arbitrary effective divisor that is supported at the cusps to do all that. But here I want to somehow stick to the case we're working with. So you have this distinguished point, and now you can look at, say, a weakly holomorphic form of weight 0 for gamma 0n. So this is some you can say it's a rational function on the modular curve x naught n. And then what you want to do is you want to assume that the order at infinity of this f is bounded by m. Yeah, so there can be a pole at infinity, but of order at most m. And you want that it's smooth at all the other cusps. So at other cusps of f should be so somehow it's always confusing with the signs. So let me just say it should be holomorphic at the other cusps. Okay, and then also you want to assume that the constant terms of f vanish at all cusps. Okay, so this is, for instance, the case for this capital J. There is just one cusp. If you choose m bigger than 1, then it's going to satisfy. I mean, M can be arbitrarily positive. If you choose it bigger than 1, then this condition is satisfied for the capital J, and yeah, and the constant term of the J, of the big J, vanishes by construction. So this is certainly satisfied for the capital J. But then, of course, for arbitrary level, you can do much more. You could also take this to be harmonic mass of weight 0, so this would work equally well. And then the point is that to this F we can associate, so proposition, there is a linear functional. Psi f from the generalized Jacobian to C that you can associate. And this is, how is this given? So you take a divisor class in this generalized Jacobian, and what you do is you evaluate the capital F at all points in the support of the divisor that are different from the distinguished point at infinity. And this gives you a well-defined map. And if you apply this map to this generating series, then you see what you get. You get a generating series whose positive coefficients are exactly the traces of the F over the Higner divisors, and whose constant and negative coefficients you can explicitly compute, and in that way you get back the result of Sage and its generalizations. Thank you.